Imagine your company just spent, I don't know, $100 million to acquire this massive, thriving competitor.
Right.
The ink is dry on the contract, the press releases are out, and you were totally ready to dominate the market.
It's a big day.
Oh, absolutely. But then, on day one, you walk into the IT department and you realize your shiny, modern, cloud-based sales system, it physically cannot talk to their 20-year-old on-premises warehouse system.
Ouch. Yeah, that's a
A
problem.
customer places an order on the website and, well, nothing happens. The warehouse doesn't even know about it. Your business is just completely paralyzed.
It's the silent killer of corporate mergers, honestly.
It really is.
Yeah.
So today, you and I are diving into the multi-billion-dollar nightmare of enterprise application integration.
Yeah, the duct-taped infrastructure that actually runs the modern corporate world.
Exactly. And the quiet revolution that's trying to fix it. Welcome to another episode discussing the research projects developed by the Applied Computing Research Group, also known as the GCA.
It's a fantastic group.
Truly. We are incredibly excited to dig into this monumental piece of software engineering research today. And right off the bat, we have to highlight the authors of the study we're analyzing. We've got Rafael Z. France, Rafael Carchuelo, Vitor Abasto Fernandez, Fernando Rosa Sequeira, Fabricio Ruz France, and Jose L. Arjona.
Yeah, and this team, they've managed to do something very rare in computer science.
Oh, how so?
Well, they've taken highly abstract academic theory and actually forged it into a practical commercial-grade tool, like something that solves a very dirty real-world problem.
Okay, let's unpack this. Because if you're listening to this and you've ever had to, say, migrate a company's database or even just try to get your email marketing software to sync up with your customer database.
It's a pain.
Right. You know the exact pain we're talking about. We are looking at a fundamental shift here, moving away from manually writing thousands of lines of fragile translation code to a future built on visual, model-driven engineering.
Which is a huge paradigm shift.
But before we get to the solution, we really need to understand the disease. So set the stage for us. What is this core problem, this enterprise application integration, or EAI?
So to understand EAI, you have to understand how a business actually buys software in the real world.
Okay.
Let's say you start a company, right? On day one, you buy an accounting package just to manage your books.
Makes sense.
Then maybe 3 years later, you launch an e-commerce site, so you buy an online shopping cart system. And then 5 years after that, you build a physical warehouse, so you install an inventory management application on a local server.
Let me guess. None of these were built by the same vendor.
Exactly. None of them use the same database architecture either.
Right, so the accounting software might be running on some proprietary Microsoft SQL server, but your web store is running in the cloud on an open source PostgreSQL database.
Yeah, and your warehouse is running some ancient Java application that only communicates over a closed local network.
So they're basically speaking entirely different languages.
Completely different ecosystems. But your business, it needs them to act as one unified organism.
Right.
When a customer clicks buy on the website, the inventory system needs to instantly reserve that item in the warehouse.
And the accounting system needs to immediately log the revenue.
Exactly. EAI is the discipline of forcing these completely disparate, independent applications to collaborate and share data in real time.
So historically speaking, how have we solved that? Like, if I'm the IT director at this hypothetical company, how do I actually get the website to talk to the warehouse?
Well, historically, you just hire an expensive team of software engineers to write custom integration scripts.
Just brute forcing it.
Pretty much. They write a piece of code that literally connects to the website's database, pulls the order data out, translates that data line by line into a format the warehouse system understands, and then pushes it across the network.
Which sounds, straightforward enough.
Yeah.
But I'm guessing it's not.
Oh, it's a total nightmare of fragility. Because the moment the website vendor updates their software and changes a single column name in their database,
Oh, wow.
like say they just change customer ID to client ID, your custom integration script just breaks.
Just from that one word change.
One word. The order doesn't transfer, the warehouse doesn't ship the item, and the engineers have to dig through thousands of lines of raw text logs at 3 in the morning to figure out why the data pipeline choked.
That sounds incredibly expensive to maintain.
It is, and worse, it locks you into your current software stack.
Oh, because if you decide you want to switch from your old warehouse system to a modern cloud-based
You
one,
have to throw away all those custom translation scripts and rewrite them entirely from scratch.
you're just held hostage by the sheer cost of rebuilding all those bridges.
Precisely.
Which brings us to the paradigm shift. This whole research paper proposes model-driven engineering, or MDE.
Right.
And the core idea here is to treat models as first-class citizens. So instead of starting by writing lines of code, you start by drawing a blueprint. The research emphasizes this strict separation between platform-independent models and platform-specific models. Help me visualize that difference.
Think of it like architecture. A platform-independent model that's basically the floor plan of a house.
Okay.
It defines the relationships. The kitchen connects to the dining room, the hallway leads to the bedrooms. It dictates the entire flow of human traffic.
Right, but it doesn't say what the house is actually made of.
Exactly.
Yeah.
It doesn't tell you if the house is built out of wood, steel, or brick. It doesn't specify if the plumbing is copper or PVC.
So in software terms, this independent model maps out the business logic. Like when a new order comes in, check the inventory, then build a credit card.
Yes, you are defining the flow of data without caring whether the final sister runs on Amazon Web Services or Microsoft Azure.
You don't even care if the data format is JSON or XML.
You don't. You're abstracting away the underlying technology so you can focus purely on the business problem itself.
Okay, I'm with you.
So once you have a perfect logical blueprint, MDE proposes that you use an engine to automatically translate that independent model into a platform-specific model.
This is where you hand the blueprint to a machine.
Yeah, you tell it, I want to build this out of Java and Oracle databases, and the machine generates the actual code.
Oh, I see where this is going. If 5 years down the line, my company decides to ditch Oracle and move everything to an open source database.
So you don't have to redesign your entire business logic.
Because I still have the platform-independent blueprint. I just tell the engine, hey, translate this blueprint into PostgreSQL this time.
You've hit the nail on the head. It drastically reduces the cost of platform migration and maximizes the reuse of your existing logic. You literally only solve the business problem once.
But hold on. I'm going to play devil's advocate here for a second.
Sure.
If this blueprint concept is so revolutionary and it saves companies from having to rewrite millions of dollars of custom code every time they switch databases, why isn't this already the industry standard?
That's the million-dollar question.
I mean, big tech companies aren't stupid. They must see the value in this.
What's fascinating here is that the industry actually does see the value. And they have poured billions of dollars into building visual integration tools. But they haven't quite built the utopia that MDE promises. And to understand why, the researchers conducted a massive review of the entire integration landscape, starting with the commercial giants.
Right. They looked at the 2019 Gartner Magic Quadrant for Enterprise Integration Platforms as a Service, or IPA. What is the acronym we'll use?
Yeah, PPAS.
And for those who don't live in the enterprise software world, Gartner is basically the Supreme Court of Technology evaluation. They look at all the vendors in a space and map them on a grid based on their ability to execute and the completeness of their vision.
And that grid gives us 4 profiles. You have niche players, visionaries, challengers, and leaders.
Break those down briefly.
Sure. Niche players might have a brilliant specific technology, but no real market reach. Visionaries see where the future is heading, but lack the infrastructure to deliver it reliably at scale.
And challengers.
Challengers have massive client bases, but are essentially just milking old technology.
But the researchers focused on the top right quadrant, right? The leaders.
Yes, the heavyweights who have both the brilliant vision and the global market presence to back it up.
And the study identifies 8 specific leaders dominating the IPS space. Let's list them. Boomi, Informatica, Jitterbit, Microsoft, MuleSoft, Oracle, SnapLogic, and Workato.
So let's look at what these platforms are actually doing, because honestly, they are incredibly sophisticated. Take a platform like Boomi, which was acquired by Dell.
Okay.
They offer a highly polished visual designer. You open a web browser, and you literally drag and drop icons to connect systems.
Wait, really? Like just drag and drop?
Yeah. You want to connect Salesforce to your internal database. You drag the Salesforce icon, you drag the database icon, and you just draw a line between them.
That's wild.
Yeah.
And Informatica is very similar, right? They rely heavily on pre-configured templates to speed up the process.
Exactly. And then you have a company like Jitterbit, which is interesting because they're trying to inject artificial intelligence into the process.
How does that work?
Well, Jitterbit uses machine learning algorithms to look at how thousands of other companies have mapped data fields between, say, Salesforce and SAP,
Oh, I get it.
right? And it proactively recommends those connections to you. It's trying to automate the intellectual labor of integration itself.
That's super smart. And obviously you can't have a list of enterprise giants without Microsoft being in there somewhere.
Of course not. They have Azure Logic apps.
They came into this specific IPS market a bit later, I think around 2016, but they brought the entire weight of the Azure cloud with them.
Yeah, they give you hundreds of out-of-the-box connectors for everything from Office 365 all the way down to legacy on-premises mainframes.
MuleSoft is another massive player, eventually acquired by Salesforce, actually.
And their architecture is slightly different. It's rooted in an open-source enterprise service bus model.
Which is what, exactly?
It essentially acts as a central nervous system for a company, allowing both cloud and local on-premise applications to just plug in seamlessly.
Got it. Then you have Oracle, basically doing what Oracle does, letting massive enterprises publish internal APIs to the outside world.
Right. And SnapLogic, who heavily emphasizes compliance.
Monitoring the data flow, right?
Yeah, constantly monitoring it to ensure you aren't violating service-level agreements or data privacy laws, which is huge in Europe with GDPR.
And finally, Workato. They are pushing into robotic process automation, or RPA.
Workato is absolutely fascinating because they blurred the line between back-end data integration and front-end user experience.
Give me an example.
So they use these pre-built recipes that allow, for example, a Slack chatbot to reach deep into a secure HR database, pull a specific employee's vacation balance, and present it right in the chat window.
And all of that is visually configured by the end user.
All visual. No coding required.
So hearing all this, these tools sound amazing. I mean, they're visual, they're drag and drop. They don't require rating thousands of lines of raw code. It sounds like they've already achieved the model-driven engineering dream we were just talking about.
It does seem that way. But the researchers didn't stop at the commercial sector. They also looked at the academic world to get the full picture.
Right. They performed a rigorous review of 15 distinct research papers published between 2010 and 2019.
Because academia is where you look to see the theoretical limits of what is actually possible. While commercial companies are building products to sell today, academia is trying to solve the fundamental computer science bottlenecks of tomorrow.
Let's give some credit to the academic pioneers here, too. You have researchers like Sun Xian and his colleagues.
Right. They realized that business rules like give a 10% discount to loyalty members, those rules change much faster than the actual business process of routing the data.
So they propose models that physically separate the rules from the routing logic.
Exactly. You also have Lee and his team building open source platforms based entirely on service orchestration. And Kavanovich and Jurek took a linguistic approach.
Oh, building their own internal domain-specific language on top of Clojure, which is a functional programming language.
And then you have some really wild architectural experiments like Balco and Barros.
What did they do?
They looked at how slow data integration can be when it's constantly writing to hard drives. So they proposed routing every single message through a shared in-memory database.
Which is brilliant for speed, I assume.
Oh, lightning fast.
Yeah.
In-memory databases operate in the system's RAM rather than on physical disks.
But RAM is volatile, right? Like, if the server loses power, all that data just vanishes.
Exactly. So Balco and Barros had to design these incredibly complex failover mechanisms to ensure transactions weren't lost if someone tripped over the power cord.
Wow. You even have highly niche solutions in the literature, like Beer and Hassan. They didn't even try to build a full integration tool.
No, they just built a mechanism that intercepts messages while they're flying between systems, feeds them into an artificial neural network, and uses AI to predict if the message contains a security vulnerability before it even reaches its destination.
That's a fantastic piece of the puzzle. But as you said, it's just one piece. The academic proposals are highly innovative, but they almost universally lack a fully integrated development environment, or IDE.
Yeah, you can't just hand a theoretical academic paper to a corporate IT team and ask them to run their multi-million-dollar business on it.
No, definitely not. But here is where the researchers pulled everything together. They looked at the billion-dollar commercial giants with their beautiful drag-and-drop interfaces, and they looked at the cutting-edge academic theories. And they found one massive, fatal flaw shared across the entire industry.
This is the real gut punch of the whole landscape review.
Yeah. Despite using visual builders, and despite using standard underlying data formats like XML, every single one of those industry platforms locks you into their proprietary ecosystem.
This is the exact crux of the problem the GCA research group set out to solve.
But wait, help me understand this. Because if I build a workflow in Boomi, Boomi exports that workflow as an XML file, right?
Correct.
And XML is an open standard. It's just text. Anyone can read it. So why am I locked in?
If we connect this to the bigger picture, you have to separate the alphabet from the language.
Okay, explain that.
XML is just the alphabet. It provides a standard way to structure tags, with opening and closing brackets. But the semantics, what those tags actually mean, is entirely proprietary to the vendor.
Ah, I get it. So Boomi might write an XML tag that literally says root message to database.
Yes, and MuleSoft might look at that exact same tag and have absolutely no idea what it means because MuleSoft's engine expects a tag called database connector path.
Wow. So there is no universal translator for the translators.
Precisely. The visual diagrams you draw in Workato only compile into Workato's proprietary XML dialect, which can only be executed by Workato's proprietary engine.
It is the ultimate irony. The whole point of enterprise application integration is to break down silos, to connect the disparate systems in your company. But by using these commercial tools, you've basically just trapped yourself in a brand new, incredibly expensive silo.
Exactly. You broke out of the Oracle silo only to get locked into the MuleSoft silo.
And remember how fast technology evolves. If you build your company's entire nervous system on one vendor's proprietary visual language today, what happens in 5 years?
Right. When a competitor releases an integration engine that is 10 times faster, twice as secure, at half the price, you can't just move your visual blueprints over.
You have to throw away years of work, manually decipher what your old integrations were doing, and rebuild them from scratch in the new tool. The migration costs are just astronomical.
So, the authors of the study realized that if they wanted to achieve true model-driven engineering, they couldn't just build another visual tool. If proprietary XML is the cage, the only way out is a language that no single vendor actually owns.
They had to build a universal blueprint grammar.
They did. And that leads us to the absolute heart of this research, the Guaraná domain-specific language, or DSL.
Guaraná is the culmination of 6 years of intensive research by the GCA group. It is a DSL specifically designed to provide a graphical notation for platform-independent EAI models.
Let's break that down for the listener because it's a lot of jargon. So domain-specific language isn't a general-purpose programming language like Java or Python, right?
Right. You can't use Guaraná to build a 3D video game or program a microwave. It is a language engineered to do exactly one thing, perfectly route data between enterprise applications.
Exactly. It is a pure conceptual language for describing data flows. It is not tied to any single execution engine.
So you are drawing the blueprint in a language that is fundamentally disconnected from the machinery that will eventually build it.
Yes. And to understand how Guaraná works, we really need to look at its fundamental building blocks. These are basically the nouns and verbs of the language. Let's walk through the pieces, starting with the most basic element of all the message.
In Guaraná, the message is the physical piece of information actually moving through the system. Think of it like a shipping container. It's not just a raw jumble of data. It has a very specific structure.
Right, it has a header.
And the header contains metadata. It has an ID number, a priority status, so the system knows if this message needs to, jump the line, and expiration dates.
Why expiration dates?
Well, so if a message gets stuck for 3 days, the system knows to just delete it, rather than processing stale data.
That makes a lot of sense. And then you have the body, which is the actual payload, the invoice data, or the customer record.
And finally, it can carry external attachments, like a PDF receipt or an image file.
So once you have a message, you need to actually do something with it. That brings us to the task. A task is the implementation of an integration pattern. This is where the actual computational work happens.
And Guaraná categorizes tasks into 3 distinct families: routers, modifiers, and transformers. Let's unpack each of these because this is where the visual logic really comes alive.
Start with the router.
A router is essentially the traffic cop. It doesn't look inside the payload of the message, and it certainly doesn't change the data itself. It just reads the header and directs traffic.
Correct. Within the router family, you have several specific tools. A filter evaluates a message against a set of rules.
So if the message meets the rules, it passes through.
Right. But if it doesn't say an invoice is missing a billing address, The filter drops the message entirely to prevent it from crashing the accounting system downstream.
You also have a replicator, which is essentially a photocopy machine. It takes one message and creates exact clones to send down different paths simultaneously.
Then you have things like correlators and mergers.
That's a correlator do.
A correlator does the opposite of a replicator. It holds on to messages until a specific group arrives. For example, if you order a laptop and a mouse, the system might generate two separate shipping messages. The correlator holds the mouse message until the laptop message arrives so they can be processed and shipped together.
Oh, that's clever. And a merger.
A merger takes messages from multiple different paths and simply funnels them into a single unified path.
Okay, so those are the routers. They move things around. Next, we have the modifiers. Now, these actually change the message, but they don't change its fundamental shape or schema. Give me an example of that.
The best example is an enricher. Imagine a message comes from the web store containing only a customer ID number and the item they bought.
Okay, but the warehouse system needs the physical shipping address, not just an ID number.
Right. So the enricher intercepts the message, reaches out to a customer database, queries the address associated with that ID, and attaches the address to the message payload before sending it on its way.
Literally enriching the data.
Exactly. And the opposite of that is a slimmer.
A slimmer. I guess it chops data off.
Yes. If a message contains a massive payload with hundreds of fields of customer history, but the next system only needs the customer's email address, the slimmer chops off all the unnecessary data to save network bandwidth.
Finally, you have the transformers. These are the heavy lifters. They fundamentally change the structure and schema of the data.
The most common is the translator. It takes a message formatted in, say, JSON and completely rewrites it into an XML structure or a flat CSV file, depending entirely on what the receiving application requires.
You also have a splitter. If an HR system generates one massive file containing the payroll data for 10,000 employees, the splitter rips that giant document apart and creates 10,000 individual messages, one for each employee.
And the aggregator does the exact reverse, waiting for a bunch of individual messages and bundling them back into a single massive report.
So you have messages, and you have tasks to process those messages. But perhaps the most crucial architectural decision the GCA group made with Guaraná isn't the tasks themselves, but what sits between the tasks.
They introduced a building block called a slot.
And this is where the language moves from being just a cool drawing tool to a piece of hardcore computer science. A slot is a buffer. It connects the output of one task to the input of the next. But why is that so critically important? I'm going to try an analogy here.
Go for it.
Let's say I'm building a plumbing system. I have a massive 4-inch pipe pushing water at high pressure. That's my fast task. And I'm connecting it directly to a tiny 1-inch pipe. That's my slow task.
Okay.
If I wire them directly together, the pressure literally blows the tiny pipe apart. The system bursts.
That is a perfect mechanical metaphor. In a traditional, poorly coded integration script, processes are often tightly coupled. Process A finishes its work and immediately hands the data to Process B.
Right.
If Process B is a slow legacy database and Process A is a lightning-fast cloud app experiencing a massive surge in web traffic, Process A overwhelms Process B.
The database locks up, the system chokes, and the application crashes entirely.
Exactly. So how does the slot fix that?
The slot acts as a reservoir tank, sitting right between the 4-inch pipe and the 1-inch pipe. In Guaraná, tasks are not allowed to communicate directly with each other, ever.
A task must output its message into a slot. The next task then pulls the message from that slot only when it is ready.
It totally decouples them. If the fast task processes 1,000 messages in a second, it just dumps them into the slot. The slow task can take its time, pulling them out of the slot one by one. The data just safely piles up in the reservoir.
Exactly. The slots act as shock absorbers, and they don't just hold data, they enforce policies. A slot can be configured as first come, first served, or it can evaluate those priority headers we mentioned earlier, pushing critical messages to the very front of the line.
By forcing all communication through these buffered slots, Guaraná inherently enforces asynchronous processing across the entire model.
And writing multi-threaded, asynchronous code from scratch in Java is notoriously difficult.
Oh yeah, you run into race conditions, deadlocks, memory leaks.
But because Guaraná is a domain-specific language tailored for this exact problem, the software engineer doesn't have to write any of that complex threading code. They just drop a visual slot between two boxes, and the language handles the physics of the data flow.
To complete the language grammar, you have ports. Ports are the gateways connecting this internal factory floor to the outside world. Entry ports bring data into the Guaraná system. Exit ports push data out.
And you have active and passive ports, too. A solicitor port actively reaches out to a third-party API and asks for information. A responder port sits passively, waiting for an outside system to ping it with a request.
Finally, you have the resource, which represents the untouchable external application like the legacy Oracle database or the Salesforce API, and the integration solution, which is the overarching container that aggregates all these elements into a single complete workflow.
Okay, so we have this incredibly robust, vendor-neutral visual language, but having a theoretical grammar on paper is only half the battle.
All right, you can't execute a whiteboard drawing.
Yeah.
A language needs a compiler. It needs an environment where an engineer can actually drag these icons around, configure them, and turn them into running software.
Which brings us to the virtual workbench, the i2 Factory platform.
Yes. While Guaraná is the academic language, i2 Factory is the commercial, cloud-based platform that brings it to life. It is an IPELA-S environment, but with a massive technical advantage. It is completely zero install.
The entire development suite, the canvas, the deployment engine, it all runs directly inside a standard web browser.
It's incredible. An engineer can be on a generic laptop anywhere in the world, log into the web portal, and have access to this massive suite of tools.
Let's walk through the core modules of i2 Factory, starting with environments.
The Environments module manages the physical execution space. i2 Factory gives you the option to run your integration logic directly on their cloud servers. But if you are a bank or a healthcare provider dealing with highly sensitive data,
Which is a huge concern. i2 Factory allows you to deploy a runtime environment directly onto your own internal servers. So the logic lives in the cloud, but the execution and the data stay safely behind your corporate firewall.
then you have the Credentials module, which is vital from a security standpoint. If your integration needs to pull files from Dropbox, post updates to Twitter, and read from Salesforce, it needs the usernames, passwords, and API keys for all those services.
In traditional scripting, lazy developers often hard-code those passwords directly into the script. It's a massive security vulnerability.
The Credentials module acts as a secure centralized vault. You store the API keys there once, and the visual model just references the vault.
You also have modules for templates, which let you save and reuse pieces of workflows you've already built, and connectors, which are the actual underlying protocol implementations, these adapters that know how to talk HTTP or FTP.
But the star of the platform is the Solutions module. This is the design canvas. This is where Guaraná really breathes.
The design canvas is where the engineer actually constructs the blueprint. You literally drag and drop the Guaraná icons, the routers, the translators, the slots right onto a grid. You draw lines connecting them, and what's brilliant is that the platform acts as an active, strict assistant.
Right, it doesn't let you build a broken machine. If I drag a translator task onto the canvas, but I forget to tell it how to translate the data, like I don't give it the mapping rules, the system flags that specific box with a red warning icon.
The entire workflow is flagged as invalid and simply cannot be deployed until every single element is perfectly configured.
Here's where it gets really interesting. Building a model is one thing. Fixing it when it goes wrong is another entirely. And anyone who has ever written software knows that debugging is where you spend like 80% of your time.
Oh, absolutely. i2 Factory includes a visual debugging mode that is, frankly, profound.
Going back to our plumbing analogy, imagine a complex chemical plant with hundreds of pipes and valves. If the water coming out the final pipe is the wrong color, the engineer usually has to guess which valve along the line is contaminated.
They have to read through thousands of lines of raw text logs, trying to find the microsecond where a comma was dropped or a variable was misaligned.
That's the grim reality of text-based debugging. But the i2 Factory debugger is like giving the engineer a magical X-ray camera.
With one click, the system shifts into debug mode. You can place a breakpoint on any specific visual task. You hit run, and the system starts processing real data. But when the data hits your breakpoint, time literally pauses. The entire integration flow just stops.
And while time is paused, the engineer can click on a slot, that reservoir tank, sitting just before the pause task. The window opens, and they can physically inspect the exact state of the message sitting inside that slot.
They can view the headers, read the payload, check the attachments. They see the data exactly as it exists at that precise microsecond.
They could look at it and say, the payload has the customer's first name, but the last name field is completely blank. The error must have happened in the task right before this one.
The psychological relief this brings to a software engineering team cannot be overstated. Catching and diagnosing errors at the visual abstraction level, rather than digging through the machine code, drastically reduces the time and money spent on maintenance.
Because you understand the flow intuitively, the overall quality of the software just skyrockets.
So we have a beautiful theory, we have a robust language, and we have an elegant web-based workbench. But I'm sure some people are skeptical. An academic paper is just words until it survives contact with the enemy. A clean lab environment is very different from the messy, duct-tape reality of corporate IT.
Which is exactly why the researchers didn't stop at building the tool. They deployed it into a live, highly complex environment just to prove it worked. This is the Portugal CIC case study. Let's talk about the victim. The partner for this trial by fire.
The researchers partnered with the Computer Science and Communications Research Center, or CIIC, at the Polytechnic Institute of Leiria in Portugal.
And the CIIC was suffering from a problem that plagues basically every academic institution on the planet: the endless, agonizing quest for grant money.
In Portugal, primary research funding comes from a government body called the Foundation for Science and Technology, or the FCT. But the FCT doesn't just hand out blank checks. The CIIC has to constantly prove they are a productive, world-class institution.
Right. They have to rigorously track, organize, and publish a record of every single paper, award, event, and partnership generated by their affiliated researchers.
And historically, how was the CIIC managing all this data?
Through pure, soul-crushing human labor. Administrators and researchers were manually tracking things down, copying and pasting data from a dozen different websites and databases, and hand-coding HTML reports to display on their public website just to satisfy the government's funding requirements.
It's the perfect EAI nightmare scenario. Let's map out the digital ecosystem they were dealing with, because it hits every branch of the ugly IT tree. They had 4 completely disconnected, disparate applications that needed to be synchronized.
First, the researchers' registry. This was their in-house local database, just tracking who actually worked at the institute.
And it wasn't a modern cloud database either. The data was stored in raw XML files, and those files were literally just sitting in a shared Dropbox folder. Very typical of legacy, ad hoc administrative processes.
Second, they had the CIIC web. This is their local content management system, the platform that actually hosted their public website where the final reports needed to be published.
Then we get to the external systems. System number 3 was Degóis. This is a massive national curriculum platform managed by the Portuguese government. Every researcher in the country is legally required to log their entire CV, all their projects and publications, into Degóis. Crucially, Degóis is accessible via a modern REST API.
For the non-technical listeners, a REST API is essentially a digital drive-through window.
Yeah.
You pull up, you hand the window a standard request like a researcher's ID number, and the window hands you back a structured package of data, like their CV.
Exactly. And the 4th system was Scopus. Scopus is owned by Elsevier, the massive academic publishing corporation. It is an international bibliography repository. It tracks global citations.
It tells you how many times a specific paper has been cited by other scientists around the world.
Right. It calculates impact factors, and Scopus also uses a REST API.
So look at the sheer chaos of this architecture. You have local raw XML files sitting in a consumer Dropbox folder. You have a local website CMS. You have a national government API, and you have an international corporate API. And the I2 Factory platform, using the Guaraná language, had to somehow orchestrate a seamless ballet between all 4 of them.
The researcher sat down and designed the final integration solution architecture. To fully automate the CIIC's workload, the visual model ended up utilizing 9 distinct ports and 24 internal tasks.
I want to trace the exact path of a piece of data through this visual map, because when you describe it step by step, it feels like watching a factory assembly line in motion. Where does the process actually kick off?
It starts at entry port P1. This port is specifically configured with the Dropbox connector and the CIC's security credentials. It reaches into the Dropbox folder and inhales the giant XML file containing the master list of all CIC researchers.
Okay, so a massive singular file enters the Guaraná factory floor, it drops into a slot, and then moves into a task called a splitter, labeled T3. The splitter looks at this giant list and violently chops it up, creating hundreds of individual tiny messages, each containing just the name and ID of a single researcher.
Those individual messages flow through slots and are routed to solicitor port P2. This is an active port. It fires those individual requests out across the internet to the Portuguese government's Degóis API. It hands the drive-through window a researcher's ID, and the API hands back a massive detailed XML file of their entire academic CV.
Now the factory floor is flooded with dozens of heavy CVs. They flow into an aggregator task, T8, which essentially sweeps them all up and bundles them into one giant, consolidated dataset of the Institute's entire brain trust.
From the aggregator, the data hits a replicator task, T10. The replicator acts as a prism. It takes that master dataset and shoots 5 exact copies of it down 5 different paths simultaneously.
Why 5 paths?
Because the website needs 5 different public reports. Each path leads to a specific translator task. One translator is programmed to sift through the CVs, extract only the data about funded projects, and format it into clean HTML. Another translator extracts only awards. The others extract events, partnerships, and advanced training.
Once those 5 HTML reports are generated by the translators, they flow to exit ports P4 through P8. These ports are also connected to Dropbox. They upload the finished HTML files straight back into a specific folder where the CIC Web CMS automatically detects them and publishes them to the internet.
Oh, boom.
The basic reporting is done.
But the workflow isn't finished. Remember the replicator task? It actually created a 6th copy of the master dataset. It sends that 6th copy down a completely different, highly complex path.
Right, because they need the global citation metrics. The 6th copy hits another splitter, T16. This splitter is surgically precise. It digs into the CVs, ignores the awards and the events, and rips out only the specific titles of the published research papers.
It creates a stream of messages containing just paper titles. Those flow to solicitor port P3. This port reaches out to the international Elsevier Scopus API. It asks Scopus, here is a paper title. How many times has it been cited globally? Scopus processes the query and returns the metrics.
The system takes those global metrics from Scopus, routes them back, and merges them with the original local data using aggregator T22. Finally, a master translator formats a beautiful, comprehensive research outcome HTML report, blending the local projects with the global citation impact. Exit port P9 uploads that final master report to Dropbox.
And just like that, the entire manual, soul-crushing workload of the administrative staff is now executed autonomously by the machine.
It's a breathtaking piece of engineering, hitting 4 entirely different platforms, blending local files with global APIs, splitting data, aggregating it, replicating it. But I have a critical question here. Let's play devil's advocate again.
All right.
In a traditional hard-coded software environment, a system this complex is essentially a house of cards. Let's say next month Elsevier decides to update the Scopus API. They change the format of the data they send back. They rename citation count to global citations. In a traditional text-based script, what happens?
This raises an important question about maintainability, which is really the true cost of software over time. In a tightly coupled JavaScript, that API change is catastrophic. The script receives the new data format, doesn't recognize global citations, and the parsing logic just throws an exception. The code crashes. The final report is never generated. The engineer then has to open the massive script, Ctrl plus F, to find every single line of code that interacts with the Scopus data, update the variable names, recompile the entire program, test it, and pray they didn't accidentally break the DeGoey integration in the process.
It's a massive blast radius for one small change.
Yeah.
So how does Guaraná handle that exact same scenario? If the Scopus API changes, what does the engineer using i2Factory actually do?
They open their web browser and log into the i2Factory canvas. They look at the visual map. They click on solicitor port P3, the exact box that talks to Scopus.
Oh.
They update the port configuration to expect the new global citations field. Then they click on the immediate translator task connected to that port, and they update the mapping rule so the system knows global citations equals citation count. And they hit deploy.
And that's it.
That is entirely it. Because of the model-driven architecture, and specifically because the slots isolate every task, the fragility is completely localized. The blast radius is contained to one single box. The Dropbox ports, the DeGoey's API logic, the splitters, the other aggregators, they remain entirely untouched. The engineer doesn't even have to look at them. The system's resilience is built into its fundamental geometry.
That is the promise of model-driven engineering fully realized. But we still have an elephant in the room. A massive technical elephant. We know the visual model works conceptually. We know it solved the university's problem. But how does dragging a blue box and connecting it to a green box actually create a running software program? How does a picture become executable code? And more importantly, for the business executives listening, how much time did it actually take a human being to sit down and build this whole thing?
These are the final 2 pieces of the puzzle, the mechanism of transformation and the rigorous time-tracking metrics the researchers recorded during development.
Let's talk about the magic trick first. Code generation. When you finish drawing your lines in i2 Factory and you hit the deploy button, what is actually happening under the hood? It's not just running a pretty animation.
No, it is executing a highly complex computer science process called model-to-text transformation. The i2 Factory platform utilizes an engine called MOF script.
Explain MOF script to me like I'm 5.
When you draw your visual model, the computer doesn't see pictures. It builds an underlying mathematical map called an abstract syntax tree. It knows that node A, which is a port, is connected to node B, a slot. When you hit deploy, the MOF script engine scans that mathematical tree. It reads the properties of every single element.
It literally reads the blueprint.
Yes, and it contains a massive library of translation scripts. So when it sees a Dropbox entry port in the tree, MOF script executes a script that automatically writes the standard Java code required to authenticate with Dropbox. When it sees a slot, it writes the multi-threaded Java code required to instantiate a memory buffer. It dynamically stitches all these snippets of code together based on the lines you drew.
And we are not talking about a lightweight toy script here. The researchers documented exactly what the engine produced for the Portugal CIAC solution. The MOF script engine automatically generated 11,129 lines of raw, executable Java code.
11,129 lines of robust, asynchronous, production-ready Java. The engine automatically creates the main process class. It writes the loops required to initialize all the slots. It generates the complex binding code that connects the input and output streams of every task to the correct slot, ensuring data flows in the right direction. It injects the proper communicators like the specific Dropbox connector class. It writes the error handling boilerplate. It does all the tedious, high-risk typing that a human engineer would normally spend days doing.
Okay, so the machine writes the code in a matter of seconds. But how long did it take the human to design the blueprint? Because if it takes an engineer 3 weeks to draw the boxes, we haven't actually saved any money. The researchers were incredibly transparent here. They meticulously tracked every single minute spent building the solution. Let's look at the metrics from Table 5 in the study.
The time tracking is deeply revealing about the current state of software engineering. First, the engineer spent 44 minutes and 28 seconds simply studying the problem.
Which makes sense. You have to read the FCT requirements, understand what the XML files look like, and figure out the API endpoints. You have to do that no matter what tool you use. You can't build a house without surveying the land.
Exactly. Next, they spent 25 minutes and 9 seconds sketching out the solution, figuring out the logic in their head or on a whiteboard. Okay, first we pull from Dropbox, then we split it, then we query Degois.
Here is where the platform speed really kicks in. The time spent physically chaining the building blocks together in the i2 Factory canvas, dragging the ports, dropping the tasks, drawing the lines, connecting them to the slots, took exactly 22 minutes and 7 seconds.
Moving from a whiteboard sketch to a fully structural digital model in 22 minutes is staggeringly fast. Setting up all the credentials and basic port configurations took an additional 2 minutes.
But then we hit the major metric, the reality check. The time spent setting up the tasks, actually opening up the visual boxes and configuring the logic inside them, took 4 hours, 25 minutes, and 33 seconds.
Yes.
So what does this all mean? Wait, hold on. 4.5 hours. We just spent the last 20 minutes praising this tool as a lightning-fast drag-and-drop miracle. If they are still spending half a day configuring the boxes, haven't we just moved the bottleneck? Why did it take 4.5 hours?
It's vital to contextualize this specific chunk of time because it reveals a profound truth about no-code and low-code platforms. The illusion of visual programming is that drawing lines is the programming. But the reality is, human business logic, deciding exactly what a piece of data means and how it should be presented, is still a manual, tedious translation process.
Dig into that. What were they doing for 4 hours?
Most of that 4.5 hours was spent specifically on the translator tasks T11 through T15. These were the tasks responsible for taking the raw XML data from the CVs and formatting it into the beautiful, final HTML reports for the website. To do this, the engineer had to write expressions using a data query language called XPath.
For those who haven't wrestled with XPath, it's essentially a navigation language for XML documents. An XML document is like a massive family tree of tags. You use XPath to tell the computer exactly which leaf on which branch to pluck. You say, go to the third child of the publication node and give me the string of text inside.
Exactly. And writing complex XPath queries to generate nested HTML tables is highly specialized, finicky work. The bottleneck wasn't the i2 Factory platform dragging them down. The bottleneck was the developer's familiarity with writing complex XPath expressions to manipulate the data strings. The human interaction with the specific data logic was the slow part.
So the translation engine works perfectly, but the human still has to tell the translator the exact grammar rules. Even still, let's zoom out and look at the aggregate time. 44 minutes to study, 25 to sketch, 22 to draw, 4.5 hours to configure, and they tracked 31 minutes and 51 seconds spent debugging using that X-ray camera we talked about.
And let's note the errors they found during that half hour of debugging. They tracked 5 minor errors within the tasks themselves, which are mostly typos in file names or slight syntax errors in those complex XPath queries. They had 1 error in a port configuration and 2 chained errors where a mistake early in the flow propagated down the line.
But the bottom line, if you tally all that up, one single engineer went from staring at a blank whiteboard trying to understand a massive administrative headache to deploying a fully automated, multi-system asynchronous integration workflow in about 6.5 hours.
And that is the true, undeniable value proposition of this research. Could a senior Java developer write a 1,129 lines of highly robust, multi-threaded, API-connected code from scratch? Yes. Would it take them 6.5 hours? Absolutely not. It would take days, perhaps weeks. And if they made a single mistake in the threading logic, the debugging alone could take another week.
Plus, as the authors note in the study, i2Factory has a compounding return on investment. Once a custom connector or a complex template is built inside the platform, it is saved in the repository. It is reusable forever. The next time the university needs to build an integration connecting to Dropbox, the port configuration time drops from 2 minutes to 0. The next time they need to parse a to-go CV, they reuse the XPath template. The platform gets exponentially faster the more you use it.
The initial effort maps the domain. Every subsequent effort just utilizes the map.
It's just phenomenal. We have gone on an incredible technical journey today. We started by diagnosing the absolute tangled nightmare of enterprise application integration, the manual coding, the fragility, the terrifying vendor lock-in that traps companies in proprietary XML cages.
We explored how the GCA research group engineered a pure, vendor-agnostic blueprint grammar with the Guaraná language. We saw how they utilized slots as asynchronous shock absorbers to prevent system failure.
We looked at the i2Factory Cloud Workbench, giving engineers an X-ray camera to debug at the speed of thought. And finally, we saw the undeniable proof, the real-world success of taking the Portugal CIIC Research Center from a manual copy-paste nightmare to a fully automated multi-API data pipeline in less than a day's work, generating over 1,000 lines of Java automatically.
It really is a compelling, commercially viable demonstration of the power of model-driven engineering.
Which leaves us with a massive and slightly intimidating implication to ponder as we wrap up today. We've proven that systems like i2Factory and Guaraná can successfully analyze a visual map and automatically generate complex, production-ready back-end code. So are we rapidly approaching an era where the very concept of a syntax error becomes a relic of the past? Will the enterprise software engineers of tomorrow even know what a programming language looks like? Or will they look more like visual systems architects, moving boxes and drawing lines, never touching a single line of raw code at all?
It's a fundamental shift in the human-computer relationship. We are moving from writing the instructions for the machine to simply describing the outcome we want and letting the machine figure out the instructions itself.
I think that's exactly where we are headed. So as you look at the digital infrastructure in your own life or your own company, the next time you see a tangled web of disconnected apps and failing APIs, ask yourself, are you still trying to manually hire translators? Or is it time to draw a new blueprint? Thank you for joining us on this deep dive into the shifting sands of software engineering. Keep exploring, keep questioning, and we'll see you in the next one.